Somehow my video doesn't start. If you can hear me, I think we need to do it without video.
Anton, I think you should be able to share your face without the screen sharing is on. So.
Okay.
Okay, just without video then. I will share my screen. Okay. So sorry, you cannot see me. Again, I hope you still remember my face. Today I will talk about two elements in 5G networks: beam selection and channel estimation. Beam selection is also about channel estimation. We will see that in the next slides. This is the second version of the slides. I uploaded this version on Dropbox as well. In this version I tailored the talk even more for the control department to cover the fundamental concepts. So I hope you will find the slides interesting. I cannot cover all the slides today, but this weekend I will upload a video on the same Dropbox links for the slides that I won't be covering today. So for those listeners who are more interested in further details, can check that link on Monday. The talk is composed of three parts. The first part will take most of the time, which are the basics. I hope you will not find many trivial information. So the second part is about beam selection paper, which I will go through briefly. The third part is about channel estimation, which I will not cover today because I thought it will be too irrelevant. So as I said, you can find some video on Monday. And later I plan to make another presentation for message passing algorithms, only on message passing algorithms. So when I record a video or I make a presentation, I can email the department. So, but I don't know when this will happen. So this slide is from the last year. Just as a reminder, we have let me open the laser point. We have this y equals to hx plus n. Y is the received signal, h is the channel matrix, and x is the transmitted signal, n is the noise. So the transmitted signal is equal to u times s. S is our transmitted symbols. We are interested in this vector eventually. We want to decode and estimate these values. And U is called a beamforming vector matrix. Each of its column affects a symbol. The first column affects the first symbol, the second affects the second symbol, and so on. So by designing the U matrix, we form a beam to transmit this symbol on the beam. We can say so like this. So this U matrix must be designed during the training phase, which is the phase right before the data transmission phase. So as a reminder again, between each antenna pair, there's a random complex number, which are all stacked in a channel matrix.
So Mustafa, this yes. M here should be an N, I think.
Oh yes, that's correct. I haven't changed them. So for this presentation, M and N from last year, this year has changed. That's correct.
What are typical dimensions, capital M and capital N?
So that is what we are going to talk about. There's a confusion here. Let's say, doesn't matter actually, M and N are a transmit number of antennas. In 5G networks, these numbers will be huge. It will be called massive MIMO. It can be 64 by 64, but in today's generation, 4G generation, it can be 4, 6, 8. So sorry for the confusion, this M and M. I will correct it. Actually, it seems Right, actually. So M is the this is the receiver part. So we have M antennas at the receiver, N antennas at the transmitter. I think it is correct.
That is correct, but
Yes.
the U is not correct.
U is not correct. Okay,
No.
U is not changed. Okay, I need
Yeah.
to correct you. Okay,
I'm just mentioning because you are going to use it later.
Yes.
It doesn't matter. Yeah.
congratulations. It's very quick observation. Great. So as I said, to design the U matrix, we need to do it during the training phase, which is before the data transmission phase. The U matrix can be designed based on a function that is dependent on the channel. In general, this is called channel state information at the transmitter. Or we can design U matrix based on a function that is not dependent on channel. So of course channel is more directly relevant because our location is Y, H, X, N. So in this case we can call it no CSIT. There is no channel state information. As an example for the first option, we can do channel estimation, channel training. So after the first step, that is when we estimate the channel matrix, we design our beamforming matrix based on this H estimate, which is called imperfect CSIT. Or for the second option, we can do beam selection, which is also called beam training. As you know, selection algorithms can be called greedy approaches. So in this option, first we create a set of beamforming options based on something. Just create a set of beamforming options, and we choose our beamforming vectors out of this set. So in this option, we are avoiding to do channel estimation. So as you see, both are about channel. We need to have H information to decode S or not, because we need to design U according to H. So perhaps we can find other ways without H information. So basically this talk is about channel estimation. If you don't want to do channel estimation, we can do beam selection. Yes, next slide. So again, before data transmission phase, we have a training phase. Here the assumption is that during the training phase and data transmission phase, the channel stays constant. So if our channel changes later, we need to do one more training phase to update our U, to update our channel estimates, etc. before the data transmission phase. Again, training phase has two options. One, either channel training or beam selection, beam training. So channel training is the conventional approach. It has been there from the beginning, but beam training is introduced and preferred for 5G mmWave networks. In this case, we have many antennas. So channel estimation can be avoided because it can be challenging with many antennas in terms of computation complexity, hardware. In fact, beam selection is also difficult because the number of beam options can increase suddenly when we have many antennas. But it has been observed that a trivial linear beam selection algorithm can be satisfactory. And as far as I know, this trivial linear beam selection algorithm is accepted in 5G standards. So for now, the approach is to avoid channel estimation and just do beam selection in the standards. And it is a really straightforward approach to do beam selection. If we have 3 transmitters and 2 users, receivers, and let's say we have only 2 beam options. So basically, access point 1 starts with trying U1 and then starts trying U2 and see which one gives the best performance metric. And after it is done with its selection, U1 and U3 are silent this time. U2 tries its own beams, and it goes on like this. When user 1, the beams are selected for user 1, we can continue for user 2. So here in this case, our metric is direct link power. that is the receive signal power. So basically what we are doing is we are choosing the beam that is more directed towards the user. As I mentioned, I won't go through the channel training part, but what I can mention here is that when we want to estimate this channel this time, we send p vector instead of x vector. This time p vector is just p vector, it has no equality. This p vector is made of pilot symbols. It's called pilots because these symbols are known by both transmitters and receivers, so that in this case our only unknown is H matrix, so we can estimate the H matrix first, and then we send X vector, our data symbols. So in 5G we will have additional signals. In addition to the microwave signals, we will have millimeter wave signals. So there's a wavelength formula which is lambda is equal to speed of light divided by frequency. This lambda is in fact a period in spatial domain. It looks like a period for sinusoidal signals that we are used to see in a time domain, but here we have c, so we are in a space domain. So basically it is the distance that signal can travel in space in full cycle. So this defines whether it is a microwave. This lambda defines whether it's a microwave or millimeter wave. So if you talk about 3-4G signals, we have 8 MHz, 1.8 GHz, 2.1 GHz frequencies. If you talk about 5G networks, we talk about 30 GHz ranges. So when we look at the wavelengths of these both signals, we see that the wavelengths are in the order of millimeter, not in the order of 1 micrometer, but for some reason, you can also check online, people also discuss same. Somehow, if the wavelength is larger than 10 millimeter, it's called microwave, but if it is from 10 to 1 millimeter, it is called a millimeter wave. So I'm going through the very basics, hopefully it is useful, interesting for everyone. So as you see from this equation and from this figure, as frequency is increased, our wavelength decreases. As I mentioned in the previous slide, this means the wavelength can travel less distance in space. It is in fact similar to x equal to vt equation, which is the distance traveled by a car. If we say 1 over f is approximately equal to time, it is like x distance speed times t. So the higher the frequency, the signal can travel less distance in space. So of course this is a disadvantage. We want the wave travel further distances. Or we can also say we need to transmit more power. We need to use more power at the transmitter for the signal to travel the same distance. Also we can say at higher frequencies equipment are more expensive and they are less stable. So what is the advantage? Then the advantage is at the higher frequencies the spectrum is less crowded, the bandwidth is wider. I will get back to these two terms in the next slide. Another advantage is we can pack more antennas in the same area, because antenna length and the distance that needs to be between the two antennas are inversely related to frequency. So if f is higher, we can have smaller antenna lengths and we can keep the distance between antennas shorter. So here you see a phone that has 4 antennas at the edges, and even Ericsson plans to have stripe antennas. These are plastic-like looking antennas that can be just put over the walls in stadium or universities. So it will be quite different in the next generation. Base stations will also have a different structure. So if I go back to spectrum and bandwidth, so our voice is also a signal. Let's quickly have a look at these definitions on a voice signal. So spectrum is the range of frequencies a signal has versus the amplitude at each frequency. These are the frequencies, and this is the amplitude axis. And bandwidth is just this distance, the maximum and minimum frequency values, the difference between these two values a signal has. So spectrum is the whole figure, whereas bandwidth is only this distance. So in the spectrum we can see the magnitude levels for each frequency, center frequency, we can see the bandwidth. So why at lower frequencies the spectrum is more crowded and bandwidths are narrower? Bandwidths need to be narrower because the spectrum is crowded at these frequencies. We cannot have contiguous wide bandwidths at lower frequencies. As an example, wireless local area networks, our Wi-Fi routers work at 2.4 and 5 GHz center frequency. Bluetooth devices work at 2.4 to 5 GHz. DAC phones, the headset and the main body talk to each other about 2 GHz. So this is a plot that we can also have at our home by downloading a software and having a Wi-Fi router and PC. This is the hotspot locations around some locations. So it is very congested. We cannot have wide bandwidths, contiguous or non-contiguous bandwidths in this region. So having 5G option in our routers is, the reason is this actually, since 2.4 GHz is congested, some users might want to choose 5 GHz. It's less congested, but then you have a disadvantage. If you have a larger house, thick walls, it won't reach to every room, etc. But you might still need maybe 5 GHz because it's less congested. So again, if every user wants to use 5 GHz, then we have wide bandwidths. As I mentioned, it is less congested area, we can have wide bandwidths, so we can use all these bandwidths all together. So this is the idea in 5G networks, this is the idea in moving up to higher frequencies. So this is just some parts of tables in 4G and 5G frequency bands. In 5G, we will have microwave frequencies from 4G, and we will have additional frequencies, millimeter wave frequencies. These are megahertz, these are gigahertz values. These are bandwidths. They are both megahertz, but the maximum here is 50. Here the max, we have 100, 200, 400 megahertz values. So basically this table and this table are almost same. There are some additional bands added. Just if the same band n is added in front of it. So in short, in 5G we will use the existing microwave frequencies. In addition, we have millimeter wave frequencies. In millimeter wave networks, we also need hybrid antennas, which I won't mention. We need both digital and analog precoders combined together, but I won't go into the details. So this is a comparison between 4 and 5G. We will have higher speeds because of wider bandwidth, less congestion. Latency will be also low. I will mention briefly later. Optical penetration and range are kind of similar things because wavelength is smaller, the range, the distance, the signal can travel is smaller, wavelength is smaller, even rain or fog, it's more subtle to even rain and fog, it's more difficult to penetrate through the walls. As a remedy to these disadvantages, 5G signals will be very directional in contrast to 4G. That is, these 5G millimeter wave signals will be very directional. So if we assume all these signals are millimeter wave signals, as you see, if we can make this signal more directed, if we can compact the energy in the main lobe, we can reach further distances by having directional beams. And we can have this focused signals by having more antennas. As I mentioned, we can pack more antennas at higher frequencies. So this is the idea. The idea is going up to higher frequencies. The distance it can travel shrink, but we can make the signal more focused. And as I will mention in the next slide, we will have more base stations, maybe every 100 meter, every 500 meter. Instead of 2 kilometer, 5 kilometer, 20 kilometer base stations, we will have mini base stations more often. But when we have focused signals, we have this disadvantage. Even the slightest movements of our heads while we are talking on the phone will be a problem because it's very focused. So there are some options. We can use all 4 antennas to track the user, or we can use 2 antennas and other 2 antennas at different 2 frequencies so they don't interfere each other. Each of the 2 antennas create different beams, and if the user moves here, we can switch instead of tracking it. So these are some techniques for remedy of head movements, for instance. So this is an example. The antennas will be in array structure. Here you see circles and rectangles. Each of them are antennas, and it will be in an array structure like 64 by 64, 128 by 128. And here you see the generations of base stations. In the beginning, there were single antenna base stations, later multiple antenna base stations, later more multiple antenna stations. Now we are in this area where it's called active antenna due to these smart techniques. And we can both call massive MIMO. It is up to us which case is massive, where the massive number starts. So base stations will also be different. And as I mentioned, in 5G, waves will be more directional. Since signals can travel less distance, we will have more mini base stations, maybe in every 500 meters instead of maximum 20 kilometers or 10 kilometers. So in the initial phase, they are going to be deployed in shopping malls, concert halls, or maybe busy downtowns. This is a bit a joke, but in 5G, your location will be more precise, so you need to be careful. Just kidding. In 4G, it is less precise. If you're in busy downtown, there are more base stations, so it can be more precise. But in 5G, they can know your location pretty much very well. Thanks to this presentation, I noticed there are many conspiracies about 5G networks. One claim, which is mentioned on whose website, that is not correct. The famous virus can travel on the waves. This is not correct. About health issues, I don't know 5G networks yet. I'm not sure, but as you also know, 4G, it is good to stay away from 4G base stations. Maybe it is the same in Sweden. Usually the telecom operators come to residential buildings. They ask to pay rental fee in return of putting their base stations on top of the buildings. I don't know if this is the case in Sweden or not. So the price can be convincing, but you really don't want to live on the last 2 floors. It's like microwave ovens. You turn on them once a while and try to stay away them, but you turn them on 24/7 and stay next to them. It won't be good. It's not a nice thing. So I will go through our beam training results This is in this work we were 3 of us. So we proposed some more advanced but still simpler beam selection algorithms, because as I mentioned, since the number of antennas are a lot in 5G networks, beam selection can be extremely complex, so we can not propose so advanced algorithms. So we propose efficient, simple algorithms, but still when the network size gets larger, such as we have more access points, more users, more antennas, the algorithm can still be overwhelming, although the algorithm is simple but effective. So then we propose machine learning algorithms that can be trained by these beam selection algorithms. This is from last year. I will skip these details. So I will just go through the numerical results. So here we are proposing some beam selection algorithms. This is the sum rate curve, bit per second per hertz, and these are the corresponding simulation durations for these results. If we pay attention to the gray curve only, we can see that we can choose either this or this algorithm, because there's a benefit by choosing this or this algorithm in terms of sum rate, and the simulation runtime doesn't increase too much. But after this point, the benefit is not too much, but the simulation runtime starts to steep up. And these two other colorful curves are for more number of random initializations and random iterations. As you know, if we start from a better point, random initialization point, we may end up at a better local optimum, so we can try multiple initializations. Iterations also means that let's say our iteration number is 2, we select all beams for all users in the first iteration, but we do one more iteration. We go back to the first user, first access point, and we choose again. So here you see that number of initializations and iterations don't help much. The reason is in these simulation results we use only single antenna users. If we have multiple antenna users, this random number of initializations and iterations increasing them might help more. But as I said, the complexity gets very huge quickly, so you might need GPUs instead of CPUs in this case. And here are the machine learning algorithms. We basically tried normal support vector machine, Gaussian kernels, SVM with Gaussian kernels, multi-layer perceptron, and random forest algorithm. So random forest algorithm gave us the best results. We could get 96 and 99% of the original sum rates that selection algorithms achieve. So this straight line is the sum rate of the selection algorithm that is used to train these machine learning algorithms. So we can get most of the sum rate, so that's a good thing. That means and the simulation runtimes are very short compared to selection algorithm runtimes. Yes, this is all about my slides. So if you have questions. So, yes, sorry. So no one has a question, I guess. I see a message.
No, not.
Okay, I see 2 messages in the chat window, but I think I need to exit this. Okay. Okay, I think those messages are not important. I don't know, I cannot see. So if there are no questions, thank you for listening.
Okay.
Thank you.
Yeah.
Okay, thank you. Hey, have a nice weekend.
Same.
You too.
Bye bye.